This is day 7 of doing math problems until your whole life member notices me. And pretty much we have a measure theory problem that we have to prove that a set of Lebesgue measure 0 is closed under countable union of sets of measure 0. And pretty much we're going to use a idea similar to Zeno's paradox. And we're going to look at the definition of Lebesgue measure zeros. So we pretty much have a set, right? A is a subset to the reals. That is one terrible R. And it has a Lebesgue measure 0 if for every epsilon is greater than 0. And there also exists a countable collection of open intervals I, n, such that A is a subset of union from n equals 1 to infinity of I to the n, or I sub n, and the sum from n equals 1 to infinity of I n. And we're going to be taking the absolute value, and it has to be less than a epsilon. And what we're going to do now is that we're going to assume that we have a countable collection of sets. Let's say E1, E2, and so on. And each of these have a measure 0. That means for pretty much every EK, and for any given epsilon greater than 0, we find a countable covering of open intervals, pretty much this I sub k n, such that we have ek is pretty much a subset or a proper subset of union n equals 1 to infinity of I n k, and the sum from n equals 1 to infinity of the absolute value of I and k. And we're going to set that less than epsilon over 2 to the k. And pretty much as you see, I'm choosing epsilon over 2 to the k as a bound for the covering of ek. And of course, like this is pretty much also like inspired by Zeno's paradox. Even if there are infinitely many sets, if each one uses up a fraction of epsilon over 2 to the k, our total epsilon, right, is pretty much going to be the sum of all these fractions that will converge to a finite number. So what we're going to do now is pretty much consider the union of all these sets, which is going to be E is pretty much equal to union from n equals 1 to infinity of E k. And since every set of E k is covered by its intervals, the union E is covered by the union of pretty much these intervals right here. Union from k equals 1 to infinity of I k n. Since we pretty much changed it, it's not going to be equal to anymore, but it is pretty much going to be in a proper subset. Now, I pretty much want to calculate the total length of all these intervals, and we're pretty much going to have pretty much the sum from n equals 1 to infinity, and the sum from k equals 1 to infinity. And we're going to have the absolute value of I k n. And pretty much for every k, the total length satisfies this other sum. Let me just clear up this. It is going to satisfy this series, the sum from n equals 1 to infinity of I k n is less than epsilon over 2 to the k. And pretty much with this, it also follows that pretty much this is going to be less than the sum from k equals 1 to infinity of epsilon over 2 to the k, right? So pretty much like the left-hand side is going to pretty much be less than the right side. And pretty much now what we have to do is just calculate this geometric series, which we know that using the geometric formula for this series, we're simply going to get that this is equal to epsilon. So this will simply just be epsilon. So pretty much like we end up having that the sum from earlier, k equals 1 to infinity of epsilon over 2 to the k, which is epsilon. We pretty much showed that for any epsilon greater than 0, there exists a covering of the union E, right? And pretty much those open intervals whose total length is less than epsilon shows that pretty much there exists covering of the union E. And by the definition of Lebesgue measure 0, that means that E, right, has measure 0. So pretty much, despite taking a countable union of an infinite number of measure 0 sets, the measure remains 0 either way. Kind of just like in Zeno's paradox, where an infinite sum of decreasing distances converges to a finite total. So pretty much this right here just shows that our set has measure 0. So that's kind of a not so heavy proof. So yeah, pretty much thank you for watching, and of course, hopefully, like if either Gura or Crony or Callie watches this, they're probably gonna have their brain be fried. But yep, thank you and bye bye.